Good day, everyone. My name is Akajiaku Ugochukwu, and I'll be presenting the paper A Machine Learning Supported Analytical Hierarchical Process and GIS Framework for Flood Risk Mapping in the Central Niger Delta. Now, this paper is presented by myself together with my colleagues Ifunanya Osondu, Anslem Otutu, Meremu Dogiye, Tarinabo Omabuwa Mene-Ejegi, Ebingiye, Nelvin, Agbozu. Flooding in the central Niger Delta remains a major environmental challenge, primarily because the region's naturally low elevation and high hydrometeorological variability drives this extreme water level. Recent studies show that these physical conditions make communities particularly vulnerable to recurring floods. In addition, rapid land use changes, including urban expansion, deforestation, and wetland conversions, have intensified the severity and frequency of these flood events. Now, other studies have also highlighted how these human-driven changes reduce natural drainage capacity and increase the exposure to flood events. At the same time, emerging machine learning techniques are demonstrating very strong predictive performance for hydrological processes in the Niger Delta. Researchers like Desmond et al. 2024, shows the machine learning models can reliably identify key environmental factors influencing flood behavior. Together, these insights underscore the need for a more robust data-supported framework for flood risk assessment and in these sensitive deltaic environments. The key challenge in flood risk assessment is that traditional decision-making tools like AHP rely heavily on expert judgment. As Sati noted in 1980, this subjectivity can reduce accuracy, especially when the criteria involve complex hydrological processes. On the other hand, machine learning methods can provide strong predictive insights, but they typically require large, high-quality data sets. In many parts of central Niger Delta, such data sets are either limited or unavailable, which are part of the challenges, which restricts the direct application of machine learning models. Now, this study addresses these limitations by combining machine learning evidence with the AHP GIS framework. The hybrid approach reduces subjectivity, improves transparency, and strengthens the reliability of flood risk mapping in data-scarce environments. The study area is located across 3 states, that's Bayelsa, Rivers State, and Delta State, and the elevation ranges from 26 to 39 meters, with extensive wetlands, tidal flats, and distributaries, just as seen on the slide. In this study, the methodology integrates machine learning, AHP, and GIS to produce a robust flood risk assessment framework. We began by selecting 9 key GIS-based criteria that are known to influence flooding across the central Niger Delta. These include terrain, hydrology, land cover, geology, and rainfall-related factors. Next, we incorporated the machine learning supported ranking, following the approach demonstrated by et al. 2024. Machine learning insights helped identify which variables have the strongest predictive influence on flood behavior, allowing us to prioritize the criteria more objectively. Using these ranked criteria, we then applied the analytical hierarchy process as established by Sati in 1980 to derive the final weights. This step provided a consistent and transparent structure for comparing the relative importance of each factor. Finally, the weighted linear combination method, as used in Moses et al. 2024, was applied in the GIS environment to integrate the weighted criteria and generate the composite flood risk map. In the data preparation stage, 9 key geospatial criteria were assembled to capture the terrain, the hydrological and environmental characteristics of the study area. This includes the digital elevation model, the slope, the drainage density, the flow accumulation, the curvature, the land use and land cover, the normalized difference water index, rainfall, and geology as documented by Jonathan and Charles in 2025. To ensure comparability across all data sets, each raster layer was standardized and reclassified into 5 ordinal classes, ranging from very low to very high flood risk. This harmonization step is essential because it allows heterogeneous criteria to be integrated consistently in the subsequent AHP and weighted linear combination processes. Machine learning studies across the Niger Delta over time consistently show that variables such as elevation, slope, NDWI, and land use land cover are dominant predictors of land or flood behaviors in the area. These factors strongly influence surface runoff, saturation, and water accumulation patterns. Now, in this study, feature importance outputs from random forest and gradient boosting models were used to guide the ranking of criteria. Now, by relying on machine learning derived evidence, we reduced the level of subjectivity normally involved in AHP. This approach not only improves the objectivity of the weighing process, but also ensures that the weighing structure is reproducible and grounded in observed hydrological patterns rather than purely expert opinions. In applying the analytical hierarchy process, we use the standard SATI 1-9 scale to perform pairwise comparisons among the 9 criteria. This scale allows us to express the relative importance of each factor in a structured and transparent way, following the method established by SATS in 1980. The resulting comparison matrix was tested for internal consistency, and the model produced a consistency ratio of 0.03. Since this value is well below the acceptable threshold of 0.10, it indicates that the judgments used in the weighing process are highly reliable. Overall, the low consistency ratio confirms that the integration of machine learning supported rankings and expert reasoning produced a stable and defensible weighing structure. So here is the criteria weights, and from this image you can see that the terrain and hydrological variables contributed the highest influence. So ML feature importance analysis produced a clear ranking that aligns with AHP weights. Now we can see the 4 classes from where the composite map identified clear zones from low, moderate, high, and very high flood susceptibility, with more of the area falling within the higher risk categories. The results from this study reinforces the critical role of terrain in shaping flood susceptibility across the central Niger Delta, as highlighted by studies. Factors such as elevation, slope, and drainage structure have a dominant influence on how water moves and accumulates in this low-lying environment. The NDWI also proved essential in identifying surface water saturation. Studies also shows that NDWI is highly effective for detecting wet, flood-prone areas, and our findings confirms this pattern, especially in wetland and riverine zones of the Delta. Overall, the hybrid machine learning analytic hierarchy process, together with the GIS model, brings greater objectivity to flood risk mapping. By combining data-driven variable importance with structured decision weighing, the framework reduces subjectivity and improves the reliability of flood risk predictions in data-scarce regions. In conclusion, the machine learning supported analytical hierarchy process and GIS framework offers a significant improvement in both the accuracy and the transparency of flood risk mapping for the central Niger Delta. By integrating ML-based feature importance with AHP weighing, the model reduces subjective bias and strengthens the overall reliability of the analysis. The resulting flood risk patterns aligns closely with historical flood behavior reported in recent studies, confirming that the approach captures real hydrological dynamics of the region. This makes the hybrid framework a valuable tool for early warning systems, disaster preparedness, and infrastructural planning, particularly in the deltaic environments where high quality hydrological data may be limited. Here are some of the references where we maximized in the course of this study. Thank you very much for listening.